some carriers think that they can resolve the contention problem by using software. Certainly, Verizon using CDC, meaning that you're using the multicast switch as a hardware to resolve the contention. So do you think that using software to resolve wavelength contention is prone to future software bugs, stuff like that?
Yeah, I don't think it's impossible to do. I don't think it's that much harder from a software perspective, but I think that the solution is nearly impossible. You can't solve a contention issue with software if you plumb out of wavelengths. As the network gets fuller, that becomes more and more difficult to say, I'm going to rearrange it somewhere else. I'm going to push that wavelength off to a different add-drop structure, or that traffic off to an add-drop structure, because you're going to run out of room sooner or later. I mean, the issue that you're trying to resolve or that you're caring for is the fact that I'm in a congested state. And software's not going to be able to do that. Software can't invent another wavelength for you or the fiber or something of that nature. It has to simply work with what it has. So I do believe it's possible to get away with it for a while, but eventually you get to that congested state, and then that's when it becomes really important to you to be able to resolve that at the physical layer and not try and strand bandwidth in the network.
Do you think that contentionless is a network with contention and a network with contentionless? The difference of a network in using SDN, and how would that be different? So meaning that if you have a network that's CDC ready, would that help the SDN to be much easier to deploy, and why?
Yeah, we believe so, because again, that path computational engine that sits as part of this SDN suite has more flexibility, has more avenues of flexibility. So it can say, well, there's no reason why I couldn't use that add-drop structure to, red wavelengths. Doesn't matter. We're in a contentionless environment, then that SDN software has to say, oh no, I've got a limitation that says I cannot do that. Therefore, I need to put that red wavelength over on a different direction. on a different add-drop structure. And again, that's a physical move. That's a physical move that we're trying to avoid. So in order to make it fully SDN capable or take advantage of that agile functionality, we want to make sure that there are no limitations that we can avoid. We're going to run into things that we can't avoid. You can't put two red wavelengths on the same fiber, physical limitation. So be it. That's the law of physics. But if we can avoid that or plan around things in the network element, then we try to take advantage of everything we can. All the tools we can get.
I see. So can you tell us a little bit about the cost saving when you use a CDC ROADM because of the OpEx saving? Just give us some idea.
Yeah, the OpEx saving, again, a good example would be network defrag or restoration. Today, what we would plan to do is in a restoration event, reusing that transmitter receiver, assigning it to a different fiber if necessary, or a different direction, or a different wavelength. And we would do that automatically. We would do that from an automated platform running in the back office system, as opposed to individuals running out in a truck and moving those fibers around. Today, that's what it would require. When there's large storms that approach a given area, we come up with a pre-plan. This is what we're going to go do. We have guys that are ready to roll out in a truck in the middle of the night and move things if need be, especially if we think that outage is going to last a while. If it's not a simple fiber break, it's something that is large storm related, big power lines that are down, and we want to reuse the transmitter receiver on a different path. It's a manual effort. And going forward, no, those guys can stay at home and we can change that remotely. And in fact, in some time, we'll even allow the network to make that change for us automatically and tell us where the new traffic is. And we believe that's a significant savings in OpEx, even if it's slightly higher in CapEx day one. Although, again, minimizing the number of transmitter receivers. If you save just a few transmitters receivers, you've more than paid for the contentionless part of that ROADM.
So what other applications are there besides network restoration?
Yeah, network restoration, network maintenance, if you want to reuse that asset, network defrag. Floating spare is one that I know you and I have talked about before. Floating spare says that I've got a spare card that I've pre-deployed, and now I can use that in the event of a failure either on the client side or the line side or at the router, because I have a fabric between them, and I can, let's say that a given transponder fails, Well, today I would generally have to have another one in its place. Well, that wavelength's no longer being used on that particular fiber. Let me just take the new one and reprogram it. I leave the client side hooked to the router exactly the same, but I've now taken this spare transmitter receiver, the expensive part, and I've deployed it on the exact same wavelength, same path, same latency. The router doesn't know any difference. We didn't have to tell it anything. That's a capability that is enabled with that agile photonic layer, something that we wouldn't be able to do in the past. Again, that would have been a truck roll to both ends because you would have had to assign a new wavelength or go out and replace that transmitter receiver, wait for the spare, things to that nature that we think we can avoid going forward if we've got this capability.
I see. So you understand our company makes multicast switches. So can you tell us a little bit about the current deployment status in Verizon's network? Is that in the metro network or is it in the long haul networks?
So just being introduced into metro and will be used in long haul as well. So it's universally, again, a tool that we want available in network. Granted, metro has a higher focus right now. A lot of our ULH network or long haul network is near maturity, but the metro network we're just introducing new platforms, and both of the platforms we're introducing take advantage of a full contentionless environment.
Is there any difference between the degrees, in the metro network and in a long haul network?
Yeah, the metros start out at 16 degrees.
Start off at
16 capable. Not all 16 get deployed day one,
sure, but
deployable are capable of 16 different degrees. Today that's 8 on the long haul environment, and generally you don't even use all 8 in a long haul environment. Where in a metro you do tend to use a lot more of them up, and it's because you're building express pipes, you're connecting disparate networks together, you're even using some of them for a large customer location or a data center of some environment where you want to make them look like they're part of, you want them photonically connected to your ROADM network so that you can avoid a back-to-back transponder if indeed there's enough capacity coming out of there. So even in places where there's not a lot of changes, if you will, I want to connect them through one of the degrees so that I can avoid a back-to-back transponder, reduce the cost and the number of network elements that's in that given circuit. Again, keep in mind that still 80% of the traffic in a metro stays metro, or some numbers vary where you're at, but still it's quite high. That metro traffic tends to stay metro, and therefore you get a lot more connectivity, and you want a lot more points connected in order to reduce the cost and eliminate those back-to-back transponders whenever possible. The multicast switches that we're buying that are part of that network design, how do you see them evolving? Lower losses, higher port counts, more granularity? Which direction do you feel they're going to go in?
Yeah, we feel that because our multicast switch is based on planar light wave circuit, which is basically a printed circuit. So it's very reliable, and it's potentially you can make the size even smaller in the near future. And we think that making the number of ports, the add-drop ports higher is possible, but certainly it's limited by the network, OSNR and stuff like that, right? So because when your port number increases, you will have the issue of adding a lot of ASE into the network. So there's a limitation. But I think in that network limitation, our multicast switch should be capable of making the next generation higher port count and also lower insertion loss. Because it has always been the case for planar light wave circuit-based AWG, array waveguide multiplexer. Over the time, its insertion loss is decreasing, size is decreasing, so it's all because it's a photonic IC. So we think that along that line, our multicast switch should be moving in a very good direction.
Well, very good. I'm glad to hear it. I look forward to it. Thank you, Winston.
Thank you.
Appreciate your time.
Thank you very much.